Hello everyone, welcome back to my channel. So in my previous video I have solved numerical related to boundary layer theory. So in this video we will see about drag and lift forces, but before we switch to drag and lift forces, let's see the applications of boundary layer theory. Please watch my earlier videos where I've explained one video on boundary layer theory and another video on numerical problems related to it. So moving on to the applications of boundary layer theory, the first applications is in aerodynamics, that is in aircrafts. So basically what happens here is that um, so in aerodynamics, the boundary layer concept refers to the thin layer of fluid flow that forms along the surface of an aircraft as it moves through the air. This layer is where the effects of viscosity are significant, leading to a velocity gradient from the surface, that is from where the velocity is zero to the free stream. So understanding boundary layer is very crucial in predicting drag and lift forces and separation of the flow, which affect the aircraft's performance, stability and efficiency. The second application is heat transfer enhancement. So the boundary layer concept in heat transfer refers to a thin region adjacent to a surface where fluid changes from zero to the free stream velocity. So by manipulating the boundary layer, such as through surface roughness or turbulence, the thermal resistance can be reduced, enhancing heat transfer by increasing the convective heat transfer coefficient. And coming to the next application is particle transportation, that is by dust blowing. So it describes how airflow near the ground or a surface forms a thin layer where velocity gradient exists. Within this boundary layer, the reduced wind speed leads to a critical condition for particles to be lifted and transported. Once particles overcome the adhesion forces, they are entrained into the airstream above the boundary layer, where they can be carried over longer distances. And the next application is to calculate the distance traveled by the golf ball. So the boundary layer concept helps in determining the air resistance and flow characteristics around a golf ball. By analyzing the transition between laminar and turbulent flow in the boundary layer, one can estimate the drag force acting on the ball, which affects its distance traveled. A smoother transition to turbulence can reduce the drag, thus increasing the distance the ball travels. Next application is flow of fluid in flat plates, what we have already discussed in the earlier videos. And the last one is drag on sphere. So a drag on sphere is in this context of drag on sphere, the boundary layer affects the flow separation point, which in turn influences the drag force experienced by the sphere. The nature of the boundary layer, uh, that is laminar or turbulent, can determine the amount of drag, with a turbulent layer typically reducing drag compared to a laminar one due to delayed flow separation. So these are the applications of boundary layer theory, and our today's video is about the calculation, the drag and lift forces introduction. So first of all, let us know what is drag and what is lift. Even when I was explaining the applications of boundary layer also, I was using the words drag and lift. So basically, what does this drag and lift mean? Say that there is a fluid medium flowing, that's a real fluid moving, and I have held a stationary object into that, or I have put a surface into the flowing medium of fluid. Then this uh, this component or this object will be subjected to forces in uh, two directions, that is one along the direction of the flow and one perpendicular to the direction of the flow. So the component of the component of force that is along the direction of the motion of the fluid is called as a drag force, and the component of force perpendicular to the direction of motion of the fluid is called as lift. I repeat, so the component of force which is parallel to the direction of motion of the fluid is called as drag, and the component of force which is perpendicular to the direction of motion of fluid is called as lift. So one can easily remember this. We know the meaning of lift. Lift is something moving in a vertical direction, so lift is perpendicular direction, and obviously drag will be the horizontal direction. Moving on to the formula related to calculating the drag force and lift force. So this is a formula CDA rho u square by 2, and lift force formula is CLA rho u square by 2, where CD and CL are the coefficient of drag and lift. Rho is the density of the fluid, U is the stream velocity with which it is flowing, and A is the cross-sectional area on which the fluid is flowing. And these two formulas are very important because in my next video I'll be doing problems related to drag and lift. So one has to calculate the values of FD and FL. So if you see in this, to calculate the values of FD and FL, I need to know the values of CD and CL first, because A value, rho and U will be given in the question, but we don't know the values of CD and CL. So to calculate the formula of values of CD and CL, these formula will be very much important. I request everyone to have a keen observation on this slide, because this slide has all the relevant formulae related to numerical problems on drag and lift. So first thing is that one has to know whether the boundary layer is laminar or turbulent. So for that, we will check with Reynolds number, as you all know. Then if it is a laminar boundary layer, to calculate the boundary layer thickness, this is a formula applied: 4.91 x by under root of rex. And then we will calculate the value of CD with the formula 1.328 by under root of REL. And tau naught, that is shear stress, is given by 0.332 rho u square by under root of REL. Okay. And if the boundary layer turns out to be turbulent, that is if your Reynolds number is coming greater than 5 into 10 power 5, it becomes a turbulent boundary layer. So once you get the turbulent boundary layer, the formula to calculate boundary layer thickness is 0.37x by Rex to the power of 1 by 5. CD is 0.072 by Rel to the power of 1 by 5, and shear stress is 0.225 rho u square into mu by rho u delta to the power of 1 by 4, where mu is the dynamic viscosity of the fluid. So please have a key note of this slide, because all this formula will be used in the problem. Okay, so one has to start solving the problem with checking with the Reynolds number. If the Reynolds number is coming out to be less than or equal to 5 into 10 power 5, you apply the formulas for this laminar boundary layer. If it is coming in greater than 5 into 10 power 5, then you apply the formulae which applicable to turbulent boundary layer. So please wait for my next video, where we will be solving numerical problems on drag and lift. So that's it for today. Hope you all understood the video, and thanks for watching.